Okay, this is Algebra 1.2, solving multi-step equations. So with your multi-step equations, you'll have more than one step to solve. And then when you're solving your multi-step equations, you still want to use inverse operations. But before that, if you can, you want to simplify each side. And we'll talk about combining like terms to be able to simplify each side. But that doesn't mean that you have to do that for every single equation. We'll also talk about what order you do the inverse operations in to isolate the variable. And then what I'll always suggest is that you check your solution. So taking a look at a few examples. Example 1, here's what I would suggest. Besides just going at it and trying to start solving the equation, if you just read the equation out loud, 3x plus 4 is equal to 9. That should give you an idea of what's being done to the variable. So the first thing that's being done to the variable is x is being multiplied by 3. That's actually the last inverse operation that I want to do. And then after x is being multiplied by 3, you're adding 4. So since adding 4 is the last operation that's being done to the variable, that's the first inverse operation that I want to do. So you basically do the inverse operations in the opposite order of what's being done to the variable. So the inverse operation of adding 4 is subtracting 4. Even though it's a multi-step equation, whatever you do to one side of the equation, you have to do to the other. So I subtract 4 from the left side, I subtract 4 from the right side. Some of you, maybe you're a little bit more comfortable with writing a line there to separate each side. Okay, you could do that as well. On the left side, 4 minus 4 is 0, so we're left with 3x. And then on the right side, 9 minus 4, 5. Now it's just what you did the other day or what you did yesterday, solving a simple equation. There's only one more step that you do to solve this equation. So it's 3x or 3 times x. The inverse operation is dividing by 3. And then on the left side, we just have x. And then I know a lot of you might want to change this to a decimal, divide 5 by 3 on your calculator, and then you get 1.6 repeating. Some of you might want to change it to a mixed number. I could leave it like this. As long as the fraction is simplified, there's nothing other than 1 that divides evenly into both 5 and 3. I could leave it like that. And I think you'll see, if I check my solution, leaving it as this fraction, even though it's an improper fraction, would be easier to check. So all I'm going to do is check this mentally or check it orally. I'm not going to write out my check, but I just want to make sure that 5/3 is the correct solution. So you substitute in 5/3 back for x here. X is being multiplied by 3. 3 times 5/3 is 15/3 or 5. And then 5 plus 4 is 9. So 5/3 checks. Might be a little bit more difficult if you made that a decimal, and then you probably have to use your calculator when you multiplied 1.6 repeating by 3. Okay, so that's why I'm leaving it as improper fraction here. All right, example 2. If I read the equation out loud, p over 4, that's p divided by 4 minus 5 is equal to negative 9. So the last thing that's actually being done to the variable is you're subtracting 5. So that's the first inverse operation that I want to use. The inverse operation of subtracting 5 is adding 5. So I add 5 to each side. On the left side, this negative 5 cancels out with the positive 5. We're left with p over 4, or p divided by 4. And then on the right side, you have to remember what happens if you add positive and negative numbers. The 9 is larger than the 5. It's negative. So your answer, or the sum, will be negative. Negative 9 plus 5 is negative 4. So the last thing that's being done to the variable here, or the only thing that's being done to the variable, is it's being divided by 4. So the inverse operation is multiplying by 4. So I multiply the left side by 4 and the right side by 4 as well. Technically, I could write this as 4 over 1. For some of you, it might be easier to write like that, because then you know the 4 is in the numerator, which would cross with this 4 in the denominator, and then we're just left with p. And then on the right side, negative 4 times positive 4 is negative 16. So again, I could check the solution. Substitute in negative 16 for p here. Negative 16 over 4, or negative 16 divided by 4, is negative 4. And then minus 5 is negative 9. So that checks. Okay, example 3. Again, reading this out loud. Here's the variable h. What's being done to the variable first is you're subtracting 5. And then all of that is being divided by 3. And then the result, or it's equal to 8. So the last thing that's being done to the variable is you're dividing by 3. That's the first inverse operation that you want to use. So inverse operation of dividing by 3 is multiplying by 3. Or like the last example, instead of just multiplying by 3, I could write that as 3 over 1. But whatever you do to one side of the equation, you have to do to the other. Everything has to balance out. So I multiply the right side of the equation by 3 as well. So this 3, which is in the numerator, would cross with this 3 in the denominator. Now we're left with h minus 5. That's over 1, but I really don't want to write it like that. It's going to be easier to solve if I just write it as h minus 5 is equal to, on the right side, 8 times 3, 24. And then to undo the minus 5, add 5 to each side. Adding 5 is the inverse operation of subtracting 5. So then the left side we have h is equal to the right side, 24 plus 5 is 29. And then I can go back and check that into the original equation, or the equation that we started with. Since h is 29, 29 minus 5 is 24. That was over or divided by 3. 24 divided by 3 is 8. So 29 checks, which means it's the correct solution. And then example 4. Before you start trying to use inverse operations, remember what we need to do to solve multi-step equations, if possible, which was not possible on any of the 3 previous examples. You want to see if you can combine any like terms. Here's what I noticed. Here's what you should notice as well. On the left side of the equation, you have 12x, and you also have 2x. Those are like terms. So it's 12x plus 2x. What you actually want to do is combine those like terms by adding the coefficients. If you have 12x's and you add 2x's to that, you're left with 14x. Don't try to think about exponents and try to make it x squared or anything like that. That's actually not until the second half of class. I would say second semester, but we're like on quarters this year, but second quarter of class. So 12x plus 2x, if it makes it easier, maybe you cross those out to know that you've combined those or already used those. Plus 4 is equal to 39. Okay, so what's being done to the variable now is x is being multiplied by 14. Then you're adding 4. The result is 39. So the first inverse operation I want to do is inverse operation of adding 4, which is subtracting 4 from each side. And we're left with 14x is equal to 39 minus 4 is 35. You want to do the inverse operation of x being multiplied by 14, so you can divide each side by 14. And here's how I'm going to write the solution. Again, instead of just taking my calculator and dividing 35 by 14, I actually don't want to leave it like that though, because 35 and 14 have a greatest common factor. The largest number that divides evenly into both 35 and 14 is 7. So I could divide 35 by 7. Whoops. 35 divided by 7 is 5. And then 14 divided by 7, 2. 5 halves. Or you could write it as 2.5 or even like 2.5. But I'm just going to leave it like that. So x is equal to 5 halves. And then just real quick, checking that. 12 times 5 halves. If you check this solution, you have to substitute in x. If I check in the original equation, not only do I have to substitute in 5 halves here for x, I have to substitute 5 halves in here for x. So I'm actually going to write some things out to keep track of things. But 12 times 5 halves, what I could do here is 12 times 5 halves. I make 12 over 1. Before I multiply those, I can do some cross canceling. 2 goes into 2 once, and then 12 6 times, and then 6 times 5 is 30. So that's 30 or 30 over 1. Plus 4, and then I'm going to write it here as well. Plus 2x, so similar to what I did with the 12, I'm going to make 2 over 1, and then I'm multiplying that by x, which is 5 halves. And basically what happens here is these 2's would just cross cancel. I could write 1's there. And that should be equal to 39. So when you multiply, if you notice this is 1 times 5 over 1, so that's just 5, and it's positive because of the plus. is equal to 39. 30 plus 4, 34, plus 5, 39. 5 halves does check, and that's the correct solution.